Hello there. In this video we're going to give a second method on how to conduct hypothesis testing for the population mean. So in the previous video we have discussed confidence intervals and how to do hypothesis testing with them. So let's briefly go over what we talked about there. Alright, so the associated picture that we typically draw is usually one of the following sorts. So usually we are conducting some hypothesis test, and associated with that is some level of confidence, and usually we represent that by C. And the reason it has this this picture is because we have this alternative that mu is equal to something, and the easiest alternative we can choose is that mu does not equal to something. So that means we're willing to accept that they're wrong if we get something large enough or small enough from our test statistic or our sample mean. That's what we're using to sort of estimate these things. So with this picture, we have a couple numbers of interest. This rate value, which is usually abbreviated by Z alpha over 2, assuming this is the normal distribution, that is. And then we have this value on the left. This is minus Z alpha over 2. And these are what we call our critical values. So from these critical values, we usually construct what we call the margin of error. So this is going to be equal to Z times alpha over 2 times sigma divided by the square root of M. So with this, we then get a similar picture. And this picture is going to pretty much look almost the same. So again, this is going to be equal to C, but these points on the axis are not z-scores. This is going to be x bar minus epsilon, and this is going to be x bar plus epsilon, with x bar in the center of what we call our confidence interval. So these are our confidence interval boundaries, namely that one and that one. All right, and pretty much how the hypothesis testing goes about. Suppose this null hypothesis mu is equal to mu0 is located somewhere to the right of our region, and you can pretty much look at it from either perspective. But remember, mu0 is in the same units as x bar minus e, but definitely this point has to have an equivalent somewhere in our z-score t-score calculation space. So of course, if this mu0 does not belong to our confidence interval, then we're going to reject the null hypothesis because our confidence interval supports that mu0 is not in there, under our level of confidence at least. So pretty much, this picture represents a different alternative that we can use for our hypothesis test. That is, do we really need to calculate our margin of error? That is, what is this number here that we can sort of compare to our critical values to sort of conduct our hypothesis test probably a little bit quicker? And this number is what we call a test statistic. And that's what this video is going to sort of discuss. It's going to discuss an alternative that is going to, give us another way of conducting a hypothesis test. So pretty much what this rule of thumb is going to be is that if the test statistic is greater than the critical value, and remember, it doesn't matter which side it is on, so technically we can say the absolute value of our test statistic. As long as that's bigger than the critical value, then we're going to reject the null hypothesis. So what exactly is this test statistic? Well, remember, this could either be a Z or a T critical value that we're comparing to. So we're going to have two test statistics for the population mean. The first is going to be the Z statistic. So this is going to be equal to the square root of n times our sample mean minus mu0 divided by sigma. So this value here corresponds to the null hypothesis. Mu is equal to mu0. So this is the number that people believe to be true, and x bar is what you're using to sort of go against that. And similarly, the t-test statistic, or which we'll just abbreviate by t-stat, is just going to be equal to the square root of n times x bar minus mu 0 divided by the sample standard deviation. So these are our two test statistics. All right, so let's work out a couple examples to sort of see how to conduct hypothesis tests for this type of thing. So example 1, and I'm going to pull the same exact numbers as the confidence interval hypothesis test to sort of compare the two. All right, so let us assume that x is normally distributed with some unknown mean mu, and let's assume that we know the standard deviation sigma to be equal to 5.2. Let us also assume that the null hypothesis that mu is equal to some number 94, and let us choose the alternative that mu does not equal to 94. Alright, so if that is the case, let us also operate under some level of confidence C. Let that be 0.92, and I leave it to you to figure out that the critical value, Z alpha over 2, is going to be 1.751. And from here, you may also want to gather your sample after you claim all these things. So let us assume our sample has characteristics that its sample mean is equal to 112 and a sample size of 43. So these are all the things that we've discussed up to this point. All right, so now let's look at the test statistic for this. So since sigma is known, and since n is relatively large, I'm going to use a Z test statistic for this procedure. So Z stat is going to be equal to the square root of n times x bar minus the hypothesized mean divided by the standard deviation of the population. So if that is the case, then Z stat is going to be equal to the square root of 43 times our sample mean, 112, minus the hypothesized mean of 94, divided by the standard deviation of the population, 5.2. And once you do all those calculations out, you're going to realize that this is equal to 22.7. So this is our test statistic. So what you're going to compare this to is you're going to go over here and compare it to this critical value Z alpha over 2. And what do we observe here? So we have our picture here, and our region of confidence is from negative 1.751 and 1.751. And what we have here is we have some test statistic over here, 22.7. It's actually more farther out because we know the standard normal usually goes from like -4 to 4, and that covers like 99.9% of the data. But nevertheless, it's going to be on the right of our critical values. So what do we see? That we see that this number is really far from our critical value. So 22.7, our Z stat value, is extremely larger than our Z alpha over 2 value, which is equal to 1.751, our critical value. So since this is the case, then we're going to reject the null hypothesis, because this test statistics, what does it describe? Well, it describes mainly the difference between our statistic x bar and what we believe or are trying to prove against mu 0. So as long as that difference is really large, this test statistic is also going to be pretty large as well. So overall, if your goal is to reject the null hypothesis, we want the test statistic, t-stat or z-stat, to be as large as possible. And of course, this depends on your sample. It has nothing to do, with anything that you usually have control over, besides your level of confidence. All right, so let's do another example just to sort of bring these things to a firm understanding. Let us again assume that x is normally distributed with mean mu and standard deviation sigma, but let's assume we don't know either of them, which is usually the most common case. Let us assume that the null hypothesis is that mu is equal to 3200, and let us choose the alternative that mu does not equal to 3200. Let us also operate under a level of confidence 0.96, and let us assume that we gather a sample and it has characteristics, x bar is equal to 3253, a standard deviation of 22.1, and a sample size of 37. So usually these things here is usually what you will calculate on your own to sort of use for your hypothesis test. Alright, so under these characteristics, if n is equal to 37, then that means the degrees of freedom is equal to 36. Now, why do I bring up the degrees of freedom? Well, the first thing is sigma is unknown. Now, you may argue that n is significantly large, but usually when one of these things are, in contrast with one another, either sigma is unknown or n is small, typically we're going to use a t distribution to do probabilities associated with confidence intervals. So with that being said, I leave to you to verify that the critical value t alpha over 2 is going to be 2.517. Alright, so from there you can calculate your confidence interval and then conduct your hypothesis test. But if we go about it from the test statistics perspective, so again, t stat is going to be equal to the square root of n times x bar minus the null hypothesis mean divided by the standard deviation of your sample. So if we plug in all of these things that we have collected, so that's going to be the square root of 37, our sample mean of 3253, the null hypothesis 3200, over the standard deviation of our sample 22.1. So once you work out those calculations, you should get test statistic of 14.6. Alright, so once you calculate your test statistic and you calculate your corresponding critical value, then you're going to compare these two things to one another. So what do we have? Well, we have our test statistic, t-stat, 14.6. Well, this number is larger, you may even say significantly larger, than the critical value t alpha over 2. Right, so our test statistic is larger than our critical value. So test statistic significantly larger than critical value. So if that is the case, then what do we do? Then that means we're going to reject the null hypothesis that mu is equal to 3200. And why do we use this notation that it's significantly larger? Well, remember, if we're really close to one another, like if my t-stat was like 2.52, yes, it is going to be larger, but they're going to be really close, so not many people will, maybe argue with your choice to reject. But the farther away it is, the better it is. So, of course, you can decide on whether this notation is appropriate to you or not. It really depends on the scenario at hand. But that's how you would go through a hypothesis test via the approach of test statistics and critical values.